Hello everyone. So welcome to the second lecture. Today we're going to be talking all about the atmosphere. So what is the atmosphere? The atmosphere is the layer of gas above the Earth's surface, which can extend over 100,000 kilometers over the Earth's surface. It has many different layers, but the majority, or over 50% of the mass of the atmosphere is located fairly close to the surface of the Earth, only 6 kilometers away. And so we're going to be talking about all these different layers and what they're made of. So the first layer is the troposphere. So the troposphere is the lowest layer closest to the Earth's surface, and it can be between 8 and 18 kilometers in thickness. And this is where all, or pretty much all, the weather occurs, especially storm clouds like this. They all are occurring within the troposphere. It's thickest in the equator, the troposphere is, and that's because the equator and the tropic regions are warmer. So the warmer the atmosphere is, the more it expands, and so the thicker that troposphere is until it reaches the tropopause, which is the name that we give for the top of the troposphere. And as you move up in the troposphere, the temperatures will decrease. So you have the warmest temperatures near the surface, where the ground and the ocean can warm up the atmosphere. And as you move higher up, as you might expect, then you have colder and colder temperatures as you move away from that heat source. And the troposphere is composed of a lot of different gases. So those gases are mainly nitrogen. These are all the gases that we breathe on a normal basis. Nitrogen, which is fairly inert, is about 78% of the atmosphere in the troposphere. And then oxygen, which is about 21%. And then you have a number of other gases, including a lot of water vapor, some noble gases, carbon dioxide, and ozone. But ozone in this layer is fairly low in concentration. That's very different than the stratosphere, which is the next layer above the troposphere in the atmosphere. And it extends about 15 kilometers to 45 kilometers in elevation. The stratosphere is very stagnant. There's not a lot of wind, almost no vertical mixing at all. So air that's there just kind of stays in place. Um, the temperature, unlike in the troposphere, increases with elevation. So the coldest region of the stratosphere is the lower area of the stratosphere. And as you go higher up, then you get to warmer temperatures. Seems a little counterintuitive, but when you think about it, the heat source for the stratosphere is the sun. And so you have a lot of particles in the stratosphere that absorb sunlight. And so that sunlight is hitting those particles and warming it up. So you don't have as much heat coming from the surface, and instead you have the heat coming from the sun. So the temperature is increasing as you get closer to the sun, further from the surface. The stratosphere, as I said, contains a lot of, or majority of the Earth's ozone, and contains the ozone layer. This layer is really important for absorbing UV radiation. Um, it's also the area where, if you remember, there was that record-breaking skydive that Felix Baumgartner. He jumped from a balloon that was all the way in the stratosphere. And the stratosphere is composed of very similar composition to the troposphere, although this ozone concentration is significantly higher in the stratosphere. So that ozone you might have heard of has a big old hole in it, the ozone hole over Antarctica. The ozone hole means that there's more UV rays that go through the atmosphere at that point. And that's caused by a gas called CFCs, chlorofluorocarbons. And this gas is composed of a lot of chlorine atoms that, when hit by the sun, can break down into individual chlorine atoms that attach to ozone, which is O3, unlike oxygen gas, that's O2. And it can strip one of those ozone atoms from the molecule, leaving just O2. And it can do this for several cycles in a row. So this can happen hundreds of times. So just a very small amount of CFCs can have a huge effect on the amount of ozone in the atmosphere. CFCs are also very strong greenhouse gases, which we'll talk about more later. And you'll notice that the ozone hole is located over Antarctica. At some points, the ozone hole was larger than the size of all of North America. It was pretty huge. And the reason why it's over Antarctica is because you kind of have a merging of a lot of ideal conditions. One, you have a lot of winds that kind of move CFCs from the equator down to the polar regions. And also you have what's called the polar vortex, which because Antarctica is an island and it's surrounded by ocean, you have a strong current of ocean currents as well as atmospheric currents that circulate around Antarctica and trap in these CFCs so that they consolidate in this region. Additionally, because Antarctica is so cold, that tends to exacerbate this process. And the ozone does not really have that big of an impact on the climate. You do have some impact because those UV rays are coming in, and so you have more absorption of sunlight in a small amount of more warming, but really the main cause of climate change, which we'll talk about later, is carbon dioxide, not ozone. So ozone and climate change are not that related. Luckily, in 1887, we had the Montreal Protocol, which was a meeting of a bunch of government leaders to discuss what to do about the ozone hole. And they significantly restricted CFC production, which is used in a lot of hairsprays and refrigerants. And after that point, the ozone hole started to recover, and you no longer had the drastic rise in the increased area of the ozone hole. And slowly but surely, the ozone hole is starting to rescind. So the next layer up in the atmosphere is called the mesosphere, which is 45 to 80 kilometers from the Earth's surface. And this layer is really cool because all meteors tend to burn up in this layer. This is the first layer that a meteor might hit, which is thick enough to actually burn up the dust that's hitting the planet. And so even though that's true, it's still very low density. The mesosphere, while still being 35 kilometers thick, it only contains about 0.1% of the mass of the atmosphere. So it's very low density. Additionally, just like the troposphere and unlike the stratosphere, the temperature decreases with elevation. So as you get higher up, then you don't have that many particles that are being warmed up by the sun, and you can get temperatures as low as negative 100 Celsius in the mesosphere, which is pretty damn cold. The next layer up is the thermosphere or the ionosphere, depending on what you're looking at. And so this is the layer above 80 kilometers in elevation. And this layer is super cool because it's where all of the aurora borealis, the northern lights, occur. And we have another reversal of the temperature gradient. Like the stratosphere and unlike the troposphere and the mesosphere, temperature increases with elevation. This is because the ionosphere is subject to solar winds. So these are winds of ionized particles that are released by the sun and hit the Earth. And these particles can ionize the hydrogen and the helium located in the ionosphere. and that ionization causes a bit of heat. And so that occurs more further away from the Earth's surface, where you have less of the magnetic pushing away of those solar winds, and so you have increased temperatures further away from the Earth's surface. That being said, it's still extremely cold, and it's almost a complete vacuum. It's very few particles that are located in this layer, only a few particles per square meter. So you would definitely not enjoy your stay if you were out in the ionosphere. Aurora borealis are super cool. So this is a northern lights that we saw in our field site. I have a field site where I do research in Greenland. So these are one of the aurora borealis that we saw there. Northern lights can be all sorts of different colors, from green, which is most common, to pinks and purples. I highly encourage you to check them out if you ever had the chance. And also, there's also a really cool new formation of northern lights that was recently just discovered, where they had these kind of vertical ribbons going across the sky. So there's new research and new findings about things going on in the ionosphere all the time. Another cool thing about the ionosphere is that it's responsible for reflecting a lot of low frequency radiation, such as radio waves or even longer wavelengths. So it provides that sort of protection due to that ionization, which is pretty cool. All right, so in the atmosphere, we have a lot of pollutants, both man-made and natural. But pollutants are anything that can be hazardous, any chemical in the atmosphere that can be hazardous to our health. So primary pollutants is a term that we use for pollutants that are emitted directly into the atmosphere. And this can include particulates. You may have heard the term being used PM50 or PM25. That's particulate matter of a particular size. And those can be emitted directly from factories or even from your tailpipe. Additionally, carbon monoxide is a dangerous pollutant, and we have to be careful for in our homes. Colorless gas. Nitrogen compounds are also often polluted from factories, and sulfur compounds, which can be particularly bad because they can cause acid rain. Secondary pollutants, on the other hand, are chemicals that happen as a degradational process in the pollution. So they're not directly polluted, but they're kind of a secondary product of what pollution that's being made. This can include photochemical smog. So that's when pollution and fog, atmospheric moisture, mixes together and forms new chemicals. And ozone. Ozone can form as kind of a secondary process in a lot of factories. You can see here that pollution occurs all over the world, but it's definitely concentrated in certain areas. Areas like China, where there's a lot of factories, and Africa, where there's a lot of deforestation and wood burning, can have a lot of pollution. But there's still a lot of pollution in North America as well. This is the most recent map we have of nitrogen dioxide. You may have heard a lot about pollutions in the news recently. A lot has been tied to how COVID has been changing the amount of pollution in the atmosphere. And unfortunately, all the reduction in pollution that occurred due to less factory and driving activity going on in China has already sprung back. And a lot of those activities are up and running again, and pollution levels have gone to their normal higher state. All this while we know that COVID-19 tends to be exacerbated by air pollution, and areas with higher air pollution tend to have worse cases of COVID-19. And at the same time, Trump has recently, just a few days ago, rolled back a lot of environmental regulations on air pollution in the Clean Air Act. So it doesn't look like those air pollutions are going to get any better in the near future. Something to keep in mind. Also, it's really important to realize that climate and weather are two different things. So in our atmosphere, we have weather events, which is just the daily occurrence of how the atmosphere is acting. The weather is what you get. The climate is what you expect. The climate is the long-term trend in the weather. So it's the average of the weather conditions. And it's really important when we move further in the class that we differentiate these two. The weather is the instantaneous event. The climate is the long-term trend. So what are some of the things that affect the climate, the controls on the climate? One of them is the general atmospheric circulation patterns. So there's winds all around the Earth, as you can see here, and they tend to have consistent patterns. And a lot of times those patterns are related to what's called the Coriolis effect. You might have heard of that term before. The Coriolis effect just means that as you move closer to the equator, an air mass is going to be moved slightly to the west. And we can relate that back to the rotation of the Earth that we talked about last lecture. And remember that the Earth is spinning faster at the equator than it is near the poles. And that's just because it's further away from that axis of rotation. And so that material has to move faster to get all the way around. It's a shorter distance covering this smaller circle near the poles. And because um, the air mass has less velocity as it moves south or towards the poles, it's going to be curved to the west, as this air tends to be faster and um, and moves further along. The inverse is also true. If you move away from the equator towards the poles, then your motion is going to be skewed over towards the east, and you're going to be kind of taking a curved path this way. And that has a big effect on atmospheric circulation. And it's what causes a lot of the trade winds that we see. These are the consistent wind patterns, such as the northeasterly trades, the southeasterly trades, and the westerlies we see in the mid-latitudes. And those trade winds, as well as kind of large-scale atmospheric circulation, causes atmospheric cells. These are kind of large atmospheric occurrences that are due to the rotation and of the Earth, as well as the exposure of the Earth to sunlight. So we have three major cells. The polar cell, which is at the top and the very bottom of the planet, the Ferrel cells, which occur in the mid-latitudes, and the Hadley cells, which are nearest to the equator. And we'll talk about that more further on. Another big control on the climate is orography, or mountains. Orographic effects can have a big impact on where water is distributed, because as a cloud moves closer to a mountain, it's going to rise, and that moisture that's caught up in that cloud won't be able to hold its moisture as much, and it's going to rain out as it rises. And so the windward side, which is the side where the clouds are coming from, is going to be wetter, whereas the leeward side, where you have a rain shadow, you have descending air, and it tends to be fairly dry. Oceans also have a big effect on climate. Areas around oceans tend to have much milder climates with less temperature extremes. That's because it takes a lot of energy to change the temperature of water, and oceans provide a lot of water vapor into the atmosphere, which can blow onto the land surface. And so as you have water vapor blowing onto the land, it starts to heat up and it will rise. And so that heat is kind of taken away and it circulates back to the ocean and sinks, where it can then circulate again. And so you have kind of much more consistent temperatures around the coast compared to further inland. One of the last things that really controls climate is altitude. So this is called, so as you move further up in altitude, as you might expect, you can see here in Hawaii, you get colder and colder temperatures. And areas that are high in altitude can have significantly colder temperatures than areas closer to sea level. And this is called a lapse rate. That's the change in temperature with elevation. It's called the lapse rate. And here we have a strong lapse rate where you have colder temperatures higher in the atmosphere. Also, latitude has a big effect. As you move closer to the poles, in the polar regions, as you all know, it's much colder and it's warmer near the equator. And that's just because the equator are pointed more towards the sun, whereas the poles are exposed to less sunlight. And you can see here that these are the average temperatures for different latitudes. And the temperature at the equator, on average, can be over 30 degrees warmer than near the poles. And you can see here that these are there's more variation in temperature too, because you have more seasonal variability in polar regions. All right, so that about wraps things up for the atmosphere. We'll be talking a lot more about it in upcoming lectures, but just a reminder, we covered the layers of the atmosphere, the troposphere, the stratosphere, the mesosphere, and the ionosphere. We also talked about the ozone hole, we talked about pollution, and we also talked about what are the type of things that control climate. All right, I'll see you guys for the next lecture.